Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist of Basic Electrical Engineering and Class 12th Physics, in our chapter Alternating Current, we'll study the concept of phase and phase difference, and this great learning video will clear all your doubt and enhance your conceptual clarity to boost your confidence and competency to understand alternating current circuits. So let's start this learning class of phase difference. An alternating current or voltage continuously change its magnitude as well as after every half cycle they alter their direction. A standard sinusoidal alternating current or voltage signal is as shown here, and it starts with zero magnitude at time instant 0, increase in a non-linear manner. Initially rate of increase is higher and then it have a decreasing rate of increase and attain positive peak, then decreases, and just like positive half cycle, a symmetrical negative half cycle is traveled. The mathematical trigonometric expression for instantaneous magnitude of voltage and instantaneous magnitude of current is written like this: V as equal to Vm sin omega t and instantaneous current is equal to Im sin omega t. And with time, when omega t argument change, the sign of omega t multiplied with respective amplitude will show the variation of instantaneous magnitude with time. Here in this mathematical relation, this omega is known as angular frequency and it is measured in radian per second, and omega when multiplied with time. This omega t measurement is an angle measure which is called argument, and when argument is considered with sine function of trigonometry, the sine of omega t when multiplied with amplitude of voltage or current gives us instantaneous voltage and current. The positive peak and negative peak got a symmetrical magnitude, and both positive half cycle and negative half cycle also got a symmetry. Complete set of positive values and negative values is called a cycle, and such cycles repeat themselves one after another. The total time duration of one cycle is called as time period, and in one time period the total angular measure or argument made is 2 pi radian. So angular frequency when multiplied with time period gives us total cyclic argument 2 pi radian, or angular frequency can be written as 2 pi divided by time period, and 1 by time period is frequency. So this angular frequency got a relation with angle and frequency, and omega is 2 pi f. In a cycle, all instantaneous magnitudes are unique and non-repetitive in nature. The condition or position of instantaneous magnitude in this cycle of standard sinusoidal alternating wave is represented in terms of time or angle, and this presentation of condition of instantaneous magnitude is known as phase. One complete cycle of standard sinusoidal alternating signal has a time duration of capital T or angle duration of 360 degree or 2 pi radian, and any position or condition of instantaneous magnitude is represented as subfraction of total time period or total angle of cycle. Here we have made 12 equal division of cycle, and we can say this position A is T by 12 time instant, or 2 pi by 12 or pi by 6 radian position, or 1/12 part of 360 degree 30 degree phase condition. So this instantaneous magnitude can be represented as phase of T by 12 time or angle of 30 degree. Similarly, this positive peak can be considered as phase of T by 4 time instance or pi by 2 radian or 90 degree angular position. Similarly, this 0 where signal is changing from positive to negative is half cycle position T by 2 pi radian or 180 degree. We preferably measured phase in degree angle, and for this measurement 0 to plus 180 degree or 0 to minus 180 degree span is used. That means this I position of negative peak is not 270 degree but it is minus 90 degree phase position. The positive half cycle and negative half cycle of sinusoidal wave got a great symmetry. This C position, phase of plus 90, got positive peak condition. Similarly, at this I position of phase minus 90 degree, the magnitude is same, peak magnitude, but with negative sign. So for positive phase angle, magnitude is positive, and for negative phase angle, magnitude is the same as that of positive phase, but the sign is negative. So at 30 degree phase, instantaneous magnitude is half of peak, and for minus 30, it is again half of peak but with negative sign. So if one understood positive half cycle, by this symmetry one can get information of negative half cycle, and this positive half cycle also got quarter wave symmetry. That means from peak to both sides, identical phase difference will fetch identical values. That means from 90 degree phase condition, if we reduce 30 degree phase, at 60 degree the instantaneous magnitude, and at 120 degree instantaneous magnitude is the same. Similarly, at 30 degree phase condition and at 150 phase condition, instantaneous magnitude is same, because this sine wave got a quarter wave symmetry across this 90 degree phase instant or positive peak. So if one can understand this positive quarter, by symmetry he can get information of another quarter, or by symmetry of positive half and negative half one can get values for negative half. A sinusoidal alternating magnitude is different from a linear uniform change. In sinusoidal signal, the rate of change is higher when instantaneous magnitude is near zero value, and it got slow rate of change near peak magnitude. In a linear uniform change, the 50% change will take place in 50% time duration, whereas in sinusoidal signal, starting from zero instantaneous value, half of peak will achieve only in 1/3 time duration, whereas in last 1/3 duration only 13.3% amount of change will take place. So it got higher rate of change when instantaneous magnitude is near zero value, and got slow rate of change when instantaneous magnitude is near peak magnitude. In a standard sinusoidal wave which starts with zero instantaneous magnitude at zero time instant and increase in positive direction, we can find out time instant for any particular instantaneous magnitude. In this numerical example, we have a sinusoidal AC voltage of 50 Hz frequency, and its amplitude or peak magnitude is 200 volt, and it's a standard sinusoidal wave which starts with zero instantaneous magnitude and increase in positive direction at t equal to 0. We have to find out time instant for instantaneous magnitude positive 100 volt first time, and we have to also find out time instant for this negative peak. So this sinusoidal wave is a standard sinusoidal wave which have zero magnitude at t equal to 0, and it increase in positive direction. So its standard mathematical equation is V is equal to Vm sin omega t, where Vm is amplitude or peak magnitude of sinusoidal variation, and it is given 200 volt. Angular frequency omega is 2 pi f, where f is frequency of sinusoidal signal 50 Hz. So omega is 100 pi radian per second. So this standard sinusoidal wave got a mathematical expression 200 sin 100 pi t, and in this expression we can find out time for any particular instantaneous magnitude. Let at time t equal to t1, this standard sinusoidal signal given by this trigonometric expression will have instantaneous value plus 100 volt first time. So in place of instantaneous magnitude we can write plus 100, and corresponding time is t1. So sin 100 pi t1 is 100 by 200 or 0.5, and 0.5 is value of sin 30. Now this 30 is in degree unit, and this argument is in radian unit. So to match things, we can make this 30 degree as pi by 6 radian, and by simple comparison, now 100 pi t1 is equal to pi by 6. Pi will get cancel out, and we will get value of t1 as 1 by 600 second, or 1000 by 600 millisecond, or 1.667 millisecond. This standard sine wave signal after completion of positive half cycle will have negative values, and we have to find out time instant t2 for negative peak instant. So in this instantaneous magnitude V equal to minus 200 volt, and time can be taken as t2, and when we solve this mathematical equation, sin 100 pi t2 comes as minus 200 by 200 or -1, and this -1 is corresponding to 270 degree, and in radian system 270 degrees 3 pi 2 radian, and we can compare 100 pi t2 argument in radian unit as 3 pi by 2, and this calculation gives us result t2 equal to 15 millisecond, and that's also true. The complete cycle got a time period of 20 millisecond, and this 3/4 of cycle will have 15 millisecond time duration. This initial t equal to 0 instantaneous magnitude can be represented by this phase argument theta, as when t is 0, the instantaneous t0 magnitude will become Im sin theta, and this theta, the phase argument, will decide t0 initial instantaneous magnitude, or we can say t0 initial instantaneous magnitude decide this phase angle theta. The general trigonometric expression for instantaneous value of alternating voltage is expressed as Vm sin omega t plus theta, where Vm is amplitude of sinusoidal voltage signal, omega is angular frequency, and this theta is phase angle of this voltage. Now this phase angle argument value theta and t0 initial instantaneous value of voltage got an interconnection, and one out of the two, if is known to us, we can find out other one. We can find out phase angle argument theta of this sinusoidal function if we know initial t equal to 0 voltage magnitude, as in this expression when t equal to 0, the t0 initial value will become Vm sin theta, and sin theta become the ratio of instantaneous t0 value and peak amplitude, and if we know that initial instantaneous value is half of peak value, sin theta is half, then it will correlate as theta equal to 30 degree, and we can express this sinusoidal voltage signal having amplitude 100, angular frequency omega, and t0 initial value half of peak as v equal to 100 sin omega t plus 30 degree, and here this 30 degree is phase angle of this voltage signal. Simple numerical can be asked on the concept of phase and general trigonometric expression of sinusoidal alternating quantity. We have given that as sinusoidal alternating voltage have a frequency of 50 Hz and amplitude 100 volt, and its t0 initial value is half of peak value 50 volt. We have to find out its initial phase angle and general trigonometric equation. So we know as sinusoidal voltage in general can be expressed as Vm sin omega t plus theta, where Vm is amplitude and it is given 100 to us. Omega is angular frequency, and angular frequency in terms of simple Hertz frequency is given as 2 pi f, and for 50 Hertz frequency given to us, angular frequency will become 100 pi radian per second, and this theta, the phase angle of the sinusoidal signal, depends upon t0 initial instantaneous value, and if we substitute the value of amplitude and angular frequency, the general expression become v is equal to 100 sin 100 pi t plus theta, and at t equal to 0, instantaneous value 50 become 100 sin theta, and this means sin theta is 0.5 or sin 30 degree. So this phase angle of sinusoidal signal having initial t0 value 50% of peak value is 30 degree, and its general expression is v is equal to 100 sin 100 pi t plus 30 degree. The initial instantaneous value of this voltage signal is 50% of its peak value, and it will attain its first positive peak just after 60 degree angular conditions, and then after it will vary its magnitude just like a standard sinusoidal wave have variation. Again, we are given a sinusoidal alternating voltage of frequency 50 Hz and amplitude 100 volt, but its initial t0 instantaneous magnitude is a negative peak minus 100 volt. We have to find out its initial phase angle argument and general trigonometric equation. Let its general trigonometric equation is v equal to Vm sin omega t plus theta. Here Vm, the amplitude of sinusoidal signal, is given 100 volt. Omega got a relation with Hertz frequency 2 pi f, and Hertz frequency is 50 Hz. So omega is 100 pi radian per second. So this general trigonometric expression of instantaneous voltage V will become 100 sin 100 pi t. We have substituted the value of voltage amplitude as 100 volt and value of omega as 100 pi radian per second, and theta is the phase angle argument, which can be obtained from its T0 initial instantaneous magnitude, which is given negative peak minus 100 volt. So at t equal to 0, instantaneous value is minus 100 volt. So V is minus 100 volt, T is 0. So minus 100 is 100 sin theta, or sin theta is minus 1, and minus 1 is correspond to theta equal to 270 degree, and in 0 to plus minus 180 degree range, 270 degree can be written as minus 90 degree, and general trigonometric expression of this voltage signal will become V is equal to 100 sin 100 pi t minus 90, or we can also write this as negative cosine wave as minus 100 cos 100 pi t. So this sinusoidal signal of peak amplitude 100 volt starting from negative peak can be written as 100 sin 100 pi t minus 90 degree, or minus 100 cos 100 pi t. Now this voltage signal, which starts from negative peak, attain its zero value after 90 degree phase span, and now onwards this variation is just like a standard sine wave. So this sinusoidal voltage variation lag standard sinusoidal voltage wave by 90 degree, and all condition of this wave, like this negative to positive 0 cross, or positive peak, or positive to negative 0, or negative peak, will occur in angular argument 90 degree after that of standard wave. Standard wave attain its initial value 0 at t0 or 0 degree phase position, whereas this wave, which lags 90 degree in phase from standard wave, attain this condition after 90 degree. So this given voltage signal wave lag standard sinusoidal wave by a phase of 90 degree. Now in this example, we have given a sinusoidal alternating voltage of frequency 50 Hz and amplitude 100 volt, and its T0 instantaneous phase is also given 90 degree. We have to find out its initial instantaneous voltage magnitude and general trigonometric equation. The general trigonometric expression of any sinusoidal voltage signal is given as instantaneous voltage small v is equal to amplitude Vm sin omega t plus theta. Here amplitude of sinusoidal signal is 100 volt given to us. Omega is angular frequency, and it is 2 pi times linear frequency 50 Hz, and it is 100 pi radian per second, and this T0 phase angle is also given 90 degree. So this would be our general expression, and at t equal to 0 we can find out instantaneous value of voltage as 100 sin 90 degree. Sin 90 degree is 1, so its initial start is from positive peak value, and this would be further variation of this sinusoidal signal. In this example, sinusoidal alternating voltage has frequency 50 Hz and amplitude 100 volt, and its initial instantaneous phase is minus 45 degree. We have to find out its initial instantaneous T0 magnitude and trigonometric equation. So the general trigonometric equation of instantaneous voltage small v is Vm sin omega t plus theta, where Vm amplitude of sinusoidal signal 100 volt is given, omega is 2 pi f, where f is Hertz frequency 50 Hz given to us, so omega become 100 pi radian per second, and this theta is minus 45 degree given to us. So when we substitute value of Vm, omega and theta in this trigonometric expression, the instantaneous voltage is given as 100 sin 100 pi t minus 45 degree. So this will become general trigonometric expression for this example, and for this, for t equal to 0, instantaneous voltage V naught become 100 sin minus 45 degree, and sin minus 45 degree is minus 0.707. When it is multiplied with 100, instantaneous T0 voltage will become minus 70.7 volt, and this voltage wave just after 45 degree got instantaneous magnitude 0, just like standard sine wave at t equal to 0. So this sinusoidal signal lags standard sine wave by 45 degree, and after 45 degree it would have the same phase position as that of standard sine wave. Standard sine wave got its first positive peak after 90 degree, whereas this signal will get that after 90 plus 45, that is 135 degree. So it lags standard sine wave by 45 degree. The general equation of instantaneous magnitude of sinusoidal alternating voltage in terms of its amplitude, Hertz frequency and phase angle theta is Vm sin 2 pi ft plus theta or Vm sin omega t plus theta. Now this omega angular frequency is given in radian per second, time t is in second, so unit of omega t is radian. And for mathematical manipulation, this summation of omega t plus theta must be in the same unit of angular measurement, radian. But for convenience, we take this first part omega t in radian unit, and this second part phase angle theta is often expressed in degree, and this convenience is followed because most of the time in place of phase we have to find out difference of phase among two sinusoidal quantity of same angular frequency, and when the difference is considered, this common term omega t will get cancelled out and will get the difference of two phase as phase difference directly in degree if phases are expressed in degree unit. So for that convenience, phase are often expressed in degree format. We can find out phase difference between two similar electrical quantities as two currents or two voltages, or we can also find out phase difference between two different quantities, one is voltage, another one is current. But all these sinusoidal function which are compared for phase difference calculation must have the same frequency or time period. We have given two sinusoidal quantity, one is voltage with amplitude Vm and standard sinusoidal format Vm sin omega t, its phase angle is considered as 0, and the second is current Im sin omega t plus theta with phase angle theta, and here this theta is phase difference between current and voltage. Now for different nature of electric circuit, we have different conditions of phase difference between voltage and current. In an ideal resistive circuit, when a standard voltage signal with T0 initial value 0 is applied, the current would have same angular frequency and same phase, and for this black wave of voltage, the brown wave represent the variation of current as shown in this diagram. Here different instantaneous values like negative to positive cross 0 value or positive peak, or 0 value from positive to negative crossing or negative peak, or while increasing half of positive peak of both black drawing voltage wave and brown drawing current wave occur simultaneously at the same time instant. At every time condition, both current and voltage have same phase conditions. When two such sinusoidal signal are precisely in step with each other, then they are said in the same phase. As here in pure resistive circuit, voltage and current are in the same phase, so they will have same phase conditions at all time instants. In an pure ideal inductive circuit, when a standard sinusoidal alternating signal shown by blue wave having T0 initial value 0 is applied, the current of same frequency but lagging voltage by 90 degree in phase will result. And if voltage is a standard sinusoidal signal with phase angle 0, then current lags voltage by 90 degree as shown here by these two yellow highlighted equation or this blue and violet wave diagram of respectively voltage and current, and here current lags voltage by 90 degree. That means at initial T0 time instant, voltage has 0 instantaneous magnitude but current has negative peak value, and after 90 degree current will attain the same phase condition as voltage has at T0 position. So current lags voltage by 90 degree, and current after 90 degree phase difference or corresponding time will attain the same phase condition as that was with voltage 90 degree before. So voltage signal will attain positive peak at 90 degree phase conditions, and this current wave will attain the same positive peak after 180 degree from start. So current lags voltage by 90 degree for all identical phase conditions. So the cyclic variation of voltage wave and current wave got identical behavior and frequency, but current variation lags in phase by 90 degree from voltage signal as expressed in these two trigonometric mathematical expression or these two voltage and current waveforms. In a resistance inductance RL circuit, the instantaneous voltage variation and current variation got same frequency but a phase difference between 0 degree and 90 degree depending upon relative value of R and L and angular frequency omega. The voltage is standard sinusoidal signal and current lags by an angle theta as shown by this black wave, and identical phase conditions of voltage and current will occur at different timing or phase positions, or current will attain or achieve the same position as that of voltage after theta phase difference. The cyclic variation of voltage shown by red wave and cyclic variation of current wave shown by black wave are identical in shape and have same frequency, but current variation lags voltage variation by an angle of phase difference theta, which is in between 0 degree and 90 degree, and we'll see that positive peak of current will occur after positive peak of voltage by an angular argument difference equal to phase difference. Now this phase difference theta is used in trigonometric expression of voltage and current, and negative sign before the phase angle of current when voltage signal is standard sinusoidal signal represent that current lags voltage by theta degree. So instantaneous magnitude of current will become identical to instantaneous magnitude of voltage after a fixed phase difference of theta. Voltage will attain zero value from positive to negative cross, and after theta angle the current will have the same phase condition. In general, it is possible for one sine wave to lead or lag another sine wave by a phase difference angle between 0 degree and 360 degree, and to determine the phase difference between two sine wave of same frequency, we can locate identical phase position on time axis, as this is 0 when signal is crossing from positive to negative, and this is 0 for black wave, and this angular span would become the phase difference between the two red and black wave as shown here. And here the one which is coming before in time leads another signal, and one that come afterwards lags the other signal. So here red wave leads black wave or black wave lags red wave. We hope this useful informative learning video has explained each and every part of phase and phase difference among sinusoidal quantities of same frequencies. Our other learning video of the same playlist are equally useful. You can use them in your studies or refer them to your friends. And if you need exam centric notes or online doubt clearing classes from our YouTube channel, do join our membership. Happy learning. Have a nice time. Thank you very much.